To review, the work-kinetic energy theorem is what we're going to turn to anytime we have friction or heat losses. And the work-kinetic energy theorem, the fleshed out equation, is down here at the bottom in yellow. The net force times the distance is equal to 1/2 times the mass times the quantity V final squared minus V initial squared. In this problem we have a 12.5 kilogram mass that starts from rest at the top of a frictionless 4 meter long 32 degree incline. So you can see the picture here. The incline is 4 meters long, it's inclined 32 degrees above horizontal, and it's frictionless, which means mu sub k is equal to 0 and the mass starts from rest. The question is, find his speed at the bottom. Well, let's step back from the work-kinetic energy theorem for a moment. Whenever we see frictionless, that suggests that there would be a good possibility that we could use the conservation of mechanical energy, because that's a fairly easy procedure. So let's do that. We're going to define the reference line as being the elevation at the bottom of the ramp, which means the height of the mass above the reference line initially will be that distance right there. Hopefully we can see by now that at the top this mass will only have gravitational potential energy, and at the bottom he'll only have kinetic energy. At the top, his gravitational potential energy is equal to m times g times h, and in this case h is equal to 4 meters times the sine of 32. So that's his gravitational potential energy at the top. At the bottom he only has kinetic energy equal to 1/2 times his mass times his final speed squared. We can very easily solve that for his final speed being 6.4 meters per second. Now, let's redo this problem if there is friction, specifically when the coefficient of friction is 0.27. Now we have to use the work-kinetic energy theorem. Let's draw a free body diagram of this mass. He would have a weight, m times g, that would be a vector that would go straight down, but that straight down mg vector is not parallel nor is it perpendicular to the surface. So I'm going to break it into a perpendicular component and a parallel component. The perpendicular component will be mg cosine theta, and the parallel component will be mg sine theta. Perhaps you remember that back when we were studying Newton's laws. There will also be a normal force, which is numerically equal to mg cosine theta, and there will be a friction force, which will be mu sub k times the normal force. Well, let's find some numbers here. Mg cosine theta is going to be 104 newtons. Mg sine theta will be 65 newtons. So the normal force will be 104 newtons. And the friction force will be 0.27 times 104, because the friction force is equal to the coefficient of friction, which is 0.27 times the normal force, 28.08 newtons. Okay, well, what's the net force then? The 104s cancel, so the net force is going to be 65 take away 28.08, which is 36.92. The distance over which that force acts is 4 meters. The initial speed is 0. The mass is 12.5. So we can solve for the final speed of 4.9. And sure enough, when there is friction, the mass has a lower speed at the end than when there isn't any friction. The work-kinetic energy theorem is one way to deal with problems having heat losses. It would be better named the work change in kinetic energy theorem, but what can you do? There are the equations for the work-kinetic energy theorem. Often, the net force is not given in the problem. To find it, use a free body diagram to help you, just like we did in solving Newton's second law problems.